everybody, and welcome to example 5 on page 6 of the workbook. Here's another example where we're going to try to prove one of the properties in the table that we had on the previous page, and in particular, they'd like us to prove property 4 of theorem 1.0.6. Okay, so let's maybe scroll back here and just remind ourselves what property 4 was. Okay, so that was this distributive property, and just so we don't have to keep flipping back and forth, I'm going to just sneak that in here, just so we can see what we're trying to prove. Okay. And for this proof, we're going to use the same strategy that we used in the previous example, a entry by entry approach. So to show that these two matrices are the same, we just need to demonstrate that corresponding entries in the matrices are the same. Okay, so we'll start by picking two matrices that have the right size for this expression to make sense. Okay, so let's let A be an m by n matrix, and B and C be n by p matrices. Okay, and just to kind of get our bearings here, let's start maybe by thinking about what we really need to show here. Okay, so we'd like to show that an arbitrary entry of this matrix over on the left, okay, which if we wrote it out would look like this, is equal to an arbitrary entry of the matrix on the right. Okay, so AB plus AC ij. Okay, we'd like to demonstrate that that's true for any row I and any column j. Okay. Well, question for you. What would be the dimension, the size of the matrix product here, A times B plus C? We can answer that question by looking at the sizes of A and then B and C. We're taking an m by n matrix and multiplying by an n by p matrix, so the size of the product should be m by p, what we're looking for. Okay, and that gives us kind of a helpful hint on how to start here. So let's start with, now let's say it this way. Okay, so for any I and j, that's going to be our row position and column position with our row position between 1 and m, and our column position between 1 and p. Okay, we got that again by noticing that our products are going to have those dimensions. Okay, we'll start with the left-hand side of our equation up here. Look at the entry in the matrix A times B plus C, in particular, the entry in the ith row and the jth column. Okay, and what we're hoping is that we can show that that's equal to this over here. All right, well, let's start by thinking about what would this be equal to? Okay, well, we're taking the matrix A and multiplying it times B plus C, so we need to think back to the definition of matrix multiplication. I'm going to sneak that in at the top of the page here. So if you page back a couple of pages here, you will notice that we defined the ijth entry of AB like this. It was a sum, okay, going from 1 to n of aik times bkj. That's the definition that we need to apply. The only difference is that instead of A and B, what we have is A and B plus C. Okay, so we're going to use A and B plus C in this definition, and it's going to look like the sum from 1 to n. Let me try to write that a little bit better. Okay, sum from 1 to n of A, I, K, and our second matrix is B plus C instead of just B, K, J. Okay, we just used definition 1.0.4. That's what this is actually up here. Okay, that we kind of snuck into our top margin here. Okay, so that gets the ball rolling for us. Okay, and then the next thing we might notice here, okay, let's rewrite the first part of this. Okay, we come to B plus CKJ, we have a definition for matrix addition, and it tells us that to add two matrices, we just have to add the corresponding entries. So here we would get BKJ plus CKJ. Okay, if you look back, you'll notice that that's definition 1.0.2. That was our definition of matrix addition. Okay, and let's see, I want to make sure I don't run out of space here. So let me try to write that a little bit smaller here. Okay, good. Okay, and the next thing that we're going to do is to distribute the AIK through. Okay, my question to you would be, can we really get away with doing that? Okay, why can we just distribute the AIK through? Because we're kind of trying to prove a distributive property here. Okay, well, the important thing to notice is that we're doing distributivity with just scalars here. Okay, all three of these numbers that I'm underlining, those are not matrices, they're just ordinary real numbers, and we know that real numbers are distributive. We can use that freely. Okay, so distributivity of scalars, which we are allowed to assume. Okay, and then just use another property of real numbers that says that when you have a finite sum like this, you can break it up into two separate sums. Okay, so I'm not going to even give a reason for that step. That's just kind of properties of arithmetic with real numbers. Okay. And take a look at the two sums that we have here. Okay, this was the very definition of, this had to do with the definition of the product of two matrices. That was our definition of what you get in the ith row and the jth column of the product matrix AB. Okay, and then similarly, this is also the definition of the product, but this time of A with C. Okay, so we just used definition 1.0.4, the definition of the product of two matrices twice, once for AB and once for AC. Okay, and then finally, you might notice that this was our definition of matrix addition. So this is AB plus AC, IJ, using definition 1.0.2 again. Okay, so as you kind of look back at our steps, we actually used some definitions twice as we wrote our proof. Okay, and now take a look at where we started and where we stopped. We started with an entry in the matrix A times quantity B plus C, and we ended up with an entry in the matrix AB plus AC. We just proved exactly what we wanted to prove. Okay, so we can finish by saying, again, since this I and J were arbitrary, we have the entire matrices, A times B plus C equals AB plus AC. Okay, and just to kind of say in words again the general strategy that we have here, we proved that these two matrices are the same by really showing one entry at a time that the entry in the first matrix is equal to the entry in the second matrix.